Let's solve leetcode 84, largest rectangle in histogram. So we're given a bunch of bar heights, and each bar has a width of 1. We want to find out what's the largest rectangle we can get and return the area of it. So in this case, the largest has an area of 10, width of 2, height 5. Another rectangle we could get has an area 8. This one has a width of 4, height of 2. Another one has a width of 6, height 1, so area 6. There's also other rectangles we could get, but these are a few of them. So if we just draw the first two bars, let's see if we can notice any patterns from them. So if you look at them, the first one is bigger than the second one. That means for this rectangle of height 2, we can't extend it any farther. Once we reach this 1, we can't extend it any farther. So the biggest rectangle we could get with height 2 is just this one right here, because there's a little hole over here, so we can't push it any farther. But for this 1, we can push, since the height is 1, we can kind of extend it towards the left a little bit, right, and use the left rectangle. And since we can't extend the height 2, we can still extend the height 1 because there's nothing coming after it that'll stop us just yet. Let's look at the opposite scenario. What would happen if the 1 came before the 2? In this case, the 1 comes first, so we can keep extending it to the right. There's nothing stopping us, right? And the 2, there's nothing coming after it just yet that'll stop us, so we can actually extend this height of 2 a little farther because there's no smaller height that comes after it, so there's no hole, right? The third case is if two rectangles were even right next to each other. In this case, we can also keep extending it, right? Because there's no hole. These rectangles are the same height. There's no smaller rectangles stopping them from being extended farther to the right. So this tells us that the current heights are going to be in increasing order because this 2 cannot be extended beyond this point. So we can only compute the area of height 2 from this width, and then we have to pop it, right? We can't extend it any farther, so we have to remove it from being considered. So now let's look at the case where all the heights are in increasing order. Notice how since they're all in increasing order, they can be extended to the right continuously, right? So this 1 over here can continue to be extended to the right. This 2 can be extended to the right. This 3 can be extended to the right. And this 4 can be extended to the right. None of them can be extended towards the left though, right? Because the height to the left is smaller, so they can't be extended to the left. But what would happen if we introduced a smaller height after? So if we introduced a 3 over here, that would mean that this 4 over here, it can't be extended any farther because there's a 3 coming after it. So all we can do is say, okay, these are the boundaries of height 4. Let's compute the area, which is going to be 4 in this case because the width is 1, and then we have to remove this from being considered, right? So we pop it. What if we introduced a 2 instead? Well, the same thing will happen. We can't extend this 4 any farther, right? So all we can say is these are the boundaries of it, right? We started back here, and then we extended all the way until we got to this 2. So compute the area, and then pop it, right? Let's look at this 3 now. We can't extend this any farther either, right? Because the 2 is less than the 3. So we can say that these are the boundaries of the 3. Let's see what the area it could have contributed was. It's 6. Maybe that's the max area. We don't know yet, but we know we can't extend this 3 any farther, so we have to pop it as well. What about this 2 over here? Well, since the new height that we got is also 2, we can keep extending it. There's no reason we can't. So we will only have to pop these two elements, the 3 and the 4, because we can't extend them any farther because now we reached a 2. Let's look at one last example to drive this point home. So now we have a 1 over here, right? So we can't extend the 4 anymore either. So we compute the area, 4, and then remove it from consideration. Also this 3, it can't be extended any further. So we compute the area, 6, and then remove it from consideration. In this case, even the 2 can't be extended any further, right? Because the 1 is too small. So we compute the area, in this case, 6, and then remove it from consideration. So in this case, we had a 1, and then we popped 3 elements from consideration, right? So notice how we are popping elements, and we're only popping the most recent elements. We're not popping an element that's in the middle. We're only popping them from the top to the bottom, from the most recent elements, right? So that tells us we should use a stack for this problem. So the stack will contain the current heights that we are considering, and we'll pop them from the top when we are no longer considering them. So now let's look at the algorithm. So I have a stack, and in the stack, I'm not just going to hold the index, and I'm not just going to hold the height. I'm going to hold both of them at the same time. So I'm holding the start index and the corresponding height. I'm also going to be maintaining what the max area is so far. So now let's start at the beginning of the array. We get element 2. So since there's nothing in the stack, we can't pop anything. Let's just add it. So at starting at index 0, we have a height of 2. Next, we get to index 1. There's a height of 1 over here, right? So now we're going to add the height 1 to our stack. But let's notice, let's look at our stack. There's a height 1 that's at the top of the stack right now. That means that this 2, it can't be extended any farther. We reached a height that was smaller than the 2. So that means we're going to pop the 2 from the stack. But before we pop it, let's just see what's the max area we could have gotten with this 2 height. So it started at index 0, right? We can see it started at index 0, and we just reached index 1. So that's the range of the width from 0 to 1. So the width is 1, the height is 2. So that means the area is 2. So far, we'll say our max area is 2 now. And now we can pop the 2 from the stack. So what's the index of this 1? Now, well, we're currently at index 1, right? So we can say that that's the index. But I'm actually going to do it a little differently. If you look at this 2, we can actually extend this 1 all the way back because we just popped this 2. That means this 1 could have been extended back by 1. So instead of saying the index of this 1, of this height 1 starts at index 1, I'm going to say it starts at index 0 because we can extend it all the way back to the 0 over here. Next, we're going to get at index 2. We have a 5, right? So we'll add that to our stack. The 5 is greater than the 1. So there's no restriction. This 1 can still be extended. So I'll just add the 5 and the corresponding index, which is 2, to the stack. Don't need to pop anything. Next, we get to index 3, right? There's a height of 6. Again, this 6 is greater than the value at the top of our stack, which is 5. So the heights are in increasing order so far, which is good. That means we don't have to pop anything. And the index we reached the 6 was at 3. That means this 5 can continue to be extended. That's why we don't have to pop the 5. Now we get to index 4. This is where the interesting stuff happens. So at this index 4, we have a height 2. The problem is this 6 now can't go any farther. We reached a 2. So this 6, which started at index 3 over here, ended up stopping at index 4. That means its width was only 1. So we have to pop it now, but before we pop it, let's get the area that it could have made. So so the width is 1, the height is 6. That means the area it could have made is 6. This is the max area that this height of 6 could have created. So we'll update our max area. 6 is greater than 2. Our max area is now 6. And let's pop this 6 from the stack. Okay, now the top of our stack is 5. But wait, 5 is greater than the 2 as well. That means this 5 can't be extended any farther. So we look at the start index of this 5, it was index 2, and we stopped it all the way at index 4. So that means its width was 2, its height is 5, so the area it created was 10. So before we pop it, let's just compute the max area that it could have created. It's 10, so we update our max area. Our max area is now 10 greater than 6, and we remember to pop this 5 from our stack. Now we look at the top of the stack, it's 1, right? 2 is greater than 1, so we don't have to pop this 1, because this 1 can continue to be extended, so we don't have to pop it, right? And what about the start index do we put for this height of 2? Can we put index 4? Well, yes, we can, but we notice that we just popped 2 elements, 6 and 5. That means this 2 can actually be extended backwards all the way to index 2, right? So instead of saying index 4 is the start value of this 2, I'm going to say index 2. Next, we reach index 5, the last element. So this height is 3. Let's put it on our stack. We see 3 is greater than 2. That means we don't have to pop the 2 from the stack. That means that this 2 can continue to be extended. There's no need to pop it. And what about the start index of this height 3? Well, we can't extend it backwards anymore, so I'm just going to say the start index is 5. If you look, we still have 3 elements left in our stack. So what do we do with them? So we have 3 elements that we didn't end up popping from the stack. What that tells us is that we were able to extend them all the way to the end of the histogram. So we still need to compute the areas we could have created from these heights. So let's iterate through them and figure that out. So let's start at this last one. At index 5, it started and it had a height of 3. So it started at index 5 and went all the way to the end of the histogram. So that means the length of it was just 1. The height is 3, so we can compute the area as having an area of 3, right? Now this area of 3 is not greater than our current max of 10, so we don't update our max. Let's go to the next element in our stack. It's index 2, height 2. That means it started at index 2 over here, and it went all the way to the end of the histogram, and it had a height of 2. So that means the width was 4, the height was 2, 2 times 4 is 8, so the area it created was 8. 8 is not greater than our max area either. The max area is 10, so we don't update the max area. The last element in our stack, index 0, height 1. That tells us it started all the way back here at index 0, and it extended all the way to the end of the histogram. So from 0 to the end is a width of 6. The height was 1, so that means the area it created was 6. This 6 is not greater than our current max area of 10 either, so that means the max area at the end is 10. So that's the result, 10. So with this algorithm, we only had to iterate through the histogram once. We had to push elements onto our stack, but we had to only push each element once and pop it once. So that means the overall time complexity is big O of n. We had to use a stack, and the stack could potentially be up to the entire size of the input array, so we did need extra memory. The memory is also going to be big O of n. Okay, now let's write the code. So we know we have to keep track of what the max area currently is, so I'm going to initially say the max area is 0. We also know we have to have a stack. In Python, we can use just a list to do that, and in my stack, I'm going to hold a pair of elements. The pair of elements is going to be an index and the height. So now let's iterate through the index and height of this heights array. Before I add it to the stack, I'm going to say the start index of this current height that we're at is just I, because we don't know if we can extend it backwards just yet. So let's now check if our stack is not empty, and if the top value in the stack and the top value's height is greater than the height that we just reached. If that's the case, that means we have to pop our stack, right? We have to pop the height, and we have to check the max rectangle we can create from that height, and we have to extend the current height that we're at backwards. So now we have to pop from the stack because this height is too great, right? So we're popping, but we have to actually retrieve the values we're popping. So we're popping an index, and we're popping the height. And we have to check if this height that we're popping could have been the max area rectangle. We're going to multiply the height by the width. We can compute the width pretty easily right now. The current index we're at is I, and the index that this height started at was what we just popped, index. So I minus index is going to be the width. And since we know that this height was greater than the current height that we're visiting, that means we can extend our start and the current, if the top value in the stack and the top value's height is greater than the height that we just reached. If that's the case, that means we have to pop our stack, right? We have to pop the height, and we have to check the max rectangle we can create from that height, and we have to extend the current height that we're at backwards. So now we have to pop from the stack because this height is too great, right? So we're popping, but we have to actually retrieve the values we're popping. So we're popping an index, and we're popping the height. And we have to check if this height that we're popping could have been the max area rectangle. We're going to multiply the height by the width. We can compute the width pretty easily right now. The current index we're at is I, and the index that this height started at was what we just popped, index. So I minus index is going to be the width. And since we know that this height was greater than the current height that we're visiting, that means we can extend our start index backwards to the index that we just popped. Now, when we actually add our element to the stack, or add our pair to the stack, we're going to add the pair start index and the height that we're visiting right now. We're not just adding I, we're adding the start index that we pushed all the way backwards. And now we remember there still might be some entries in our stack left. So these were able to be extended all the way to the end of the histogram, so we still have to compute their heights. And we can do that pretty easily. So we potentially update our max area. The height is just what's stored in the stack, so height multiplied by the width. We can compute the width pretty easily. We know that these were extended all the way to the end of the histogram, so we can get the length of the histogram subtracted by the start value I that was stored in the stack. And now all we have to do is return our max area. I, and the index that this height, if this height that we're popping could have been the max area rectangle. To the stack, I'm going to say the start index is going to be an index and the height. So now let's iterate through the index and height of this heights array. Before I add it to the stack, I'm going to say the start index of this current height that we're at is just I, because we don't know if we can extend it backwards just yet. So let's now check if our stack is not empty, and if the top value in the stack and the top value's height is greater than the height that we just reached. If that's the case, that means we have to pop our stack, right? Right? We have to pop the height, and we have to check the max rectangle we can create from that height, and we have to extend the current height that we're at backwards. So now we have to pop from the stack because this height is too great, right? So we're popping, but we have to actually retrieve the values we're popping. So we're popping an index, and we're popping the height. And we have to check if this height that we're popping could have been the max area rectangle. We're going to multiply the height by the width. We can compute the width pretty easily right now. The current index we're at is I, and the index that this height started at was what we just popped index. So I minus index is going to be the width. And since we know that this height was greater than the current height that we're visiting, that means we can extend our start index backwards to the index is going to be the width. And since we know that this height was greater than the current height that we're visiting, that means we can extend our start index backwards to the index that we just popped. Now, when we actually add our element to the stack, or add our start index backwards to the index that we just popped. Now, when we actually add our started at was what we just popped index. So I minus index is going to be the width. And the current index we're at is I, and the index that this height started at was what we just popped index. So I minus index is going to be the width. And since we know that this height was greater than the current height that we're visiting, that means we can extend our start index backwards to the index that we just popped. Now, when we actually add our element to the stack, or add our pair to the stack, we're going to add the pair start index and the height that we're visiting right now. We're not just adding I, we're adding the start index that we pushed all the way backwards. And now we remember there still might be some entries in our stack left. So these were able to be extended all the way to the end of the histogram, so we still have to compute their heights. And we can do that pretty easily. So we potentially update our max area. The height is just what's stored in the stack, so height multiplied by the width. We can compute the width pretty easily. We know that these were extended all the way to the end of the histogram, so we can get the length of the histogram subtracted by the start value I that was stored in the stack. And now all we have to do is return our max area. And it works perfectly. I think this is the most intuitive solution, at least from my perspective, for this problem. Storing, I think, the start index and the height in the stack makes it a little easier.
Hey everyone, today we are going to solve the leet code question, largest rectangle in histogram.